let's start. So yesterday we started the subject of fluid mechanics, right? And we discussed some applications. So you told me the scope of the subject, that what we are going to do is we are going to study the mechanical behavior of fluids. We are going to apply forces and we will see what is the deformation, what is the motion, right? And then we discussed that this study is actually going to help us design or understand a lot of systems. You can understand cardiovascular system, respiratory system, and then design the corresponding devices. You can design the dam or layout of a hydroelectric power plant and all the devices in it, like pumps, turbines, gates, etc. You can design systems like even air conditioners and heaters, refrigerators with it, and a lot of places are there where this subject is used. So today we are going to start the main hardcore portion of the course. That is the portion which is required in the GATE exam. Okay, so we will start with the very first chapter, and as you can see, the topic is what is fluid. So basically we want to understand the definition of fluid. Okay, so write down definition of fluid, or you can also mark it as what is fluid. So I think whenever we say fluid, fluid refers to liquids like water, oil, etc., right? Shampoo. And it also refers to gases like air, oxygen, steam, whatever it is, right? But in overall, fluid is a category of something bigger. Fluid is a type of a bigger term, a broader term, that is matter. Is that right? Hai? Fluid is a type of matter. So it's like that initially during the like 3000 or 4000 years back, so before the birth of Christ, so Germans and Greeks, Romans, they were the more civilized organizations. They had more hand in engineering. So what they believed is that anything around us, which you call as matter, matter is made of 4 elements. That is earth, water, air and fire. Okay. And later on they also added one more element, that is ether. So what they said is that if we are talking of this solid is made of earth, water, air and fire. Similarly, anything else is made of these 4 elements. And obviously this understanding was not so good. It was a pathetic explanation of matter. So later on, as our understanding improved, we realized that everything is made of 3 fundamental particles. Those are electrons, protons and neutrons. So what happens is that protons and neutrons, which have the size of 10 raised to power minus 15 meters. Okay, please note. Shridhar, you are right. In Indus Valley civilization, we called it as 5 elements. Chinese also called it as 5 elements. But if we talk of engineers, they were a little better than us in terms of physics. Okay, so that's why I took their reference. So when we talk of protons and neutrons, their size is 10 raised to power minus 15 meters. Please check the size of proton. Okay, so when I say 1 mm is this much. This much is 1 mm. Okay, and I think it will be very difficult for you if you are talking of 0.1 mm. You cannot see 0.1 mm very easily. What is 0.1 mm? 10 raised to power minus 4 meters. So it is difficult for us to see even 10 raised to power minus 4 meters. And I am talking of something which is 10 raised to power minus 15 meters. So protons, neutrons, what they do is they form groups. So they form a single group that is known as nucleus. Around the nucleus, the electrons are revolving. So that becomes an atom. Now different atoms, they share electrons to form molecules. Okay, so in every substance, protons and neutrons will form nucleus. Electrons will revolve around it to form atoms, and atoms will share electrons to form molecules, right? Now when you talk of atoms, atoms have a size of 10 raised to power minus 10 meter. This is the size of an atom, or you can say molecule. Okay, and I hope you remember that in any substance, solid, liquid or gas, there is some distance between the atoms, right? So in solids, the distance is of the same order. This is the order of distance between 2 atoms of a solid. Okay, all of you, you can note these values in rough if you want. So our understanding grew that everything is made up of these fundamental particles. So say for example, if I talk of H2O, okay, H2O, gel जिसको आप बोलते हैं. So H2O is hydrogen atom and oxygen atom which are sharing electrons. Similarly, carbohydrates, that is carbon and hydrogen and nitrogen elements which are sharing electrons, atoms which are sharing electrons. So everything is made of this. But if you talk particularly of H2O, H2O can exist as ice, which is also solid. It can exist as water, which is a liquid. It can exist as steam also, which is a gas. So what I'm trying to say is H2O means matter. A matter can exist as solid also, liquid also, gas also. And liquid and gases, we call them as states of matter. Okay. So any idea in total how many states of matter are there in total? Any idea? 5. Okay, very good. All of them are saying 5. So I think you guys are talking about solid, liquid and gas. These are 3 states of matter. Then one state of matter is plasma also. So what is plasma? I think plasma is charged particles, right? If there is a gaseous medium which has charged particles, you call it as plasma. And plasma is especially found in the outer layer of the Earth's atmosphere. Yes, ionized gas. Okay, so it is found in the outermost layer of the Earth's atmosphere. So all those engineers who are involved in taking spacecrafts to the space or bringing them back to the Earth, okay, so they have to understand that when the spacecraft is coming back to the Earth's atmosphere, there will be some friction forces between the plasma and the spacecraft. So what are those friction forces? So those engineers try to understand plasma. Similarly, there are some engineers who design welding systems. They have to also understand about plasma. So you said 5, so there will be fermionic condensates, I think this is what you want to say. But actually a lot of states of matters are there. I mean, in terms of quantum physics nowadays, there are not only 3 states of matter, but actually more than 20 states of matter are there. Say for example, some of them are here. So you can see excitonium, photonic matter, fermionic condensates, quark matter, quark-gluon plasma. Okay, so different states of matter are there. But we are going to talk about the left one only, that is solid, liquid and gas. We are basic engineers, we will talk about solid, liquid and gas only. In between there is something that is Bose-Einstein condensate, which I've highlighted. So basically Satyendra Nath Bose, he was the guy who found this along with Albert Einstein. These two guys discovered Bose-Einstein condensates. Okay, so a lot of states of matter are there, but we as basic engineers, we are going to talk about only solid, liquid and gas. So I think from the very beginning, like 8th, 9th and 10th classes, we are talking about them, what is solid, what is liquid, what is gas. So let me remind very fast. So when we say solids, in case of solids, the molecules are very close to one another, right? So when molecules are very close to one another, I mean the distance between the molecules is 0.5 into 10 raised to power minus 10 meter, very less distance. So the forces between them will be very strong. Forces of attraction between them will be very strong. So molecules are nearly fixed at their position. So once they are nearly fixed at their position, they will not, basically the molecules are fixed at position, so the whole body will become rigid. So this is a rigid body, right? Why? Because the molecules are fixed at their positions. But when we talk of liquids, the molecules are a little apart. So distance between them is like a little greater than that of solid. So in case of solid, if it is half into 10 raised to power minus 10, then in case of liquids, it might be 1.5 into 10 raised to power minus 10. As a result, the forces are weak and the molecules can move around. So if the molecules can move around, the shape of the substance will not be fixed. Now check, this is your water bottle. In the water bottle, you can see the shape of water. If I tilt it, the shape of water will change, right? So since the molecular forces of attraction are weak, that's why the shape is not fixed. But when we talk of gases, the distances between them are very large. Okay, they are in the order of 10 raised to power minus 7 or minus 8 meters, just as an example. Okay, so it is greater than this one. So forces between them are weak and as a result the molecules are moving around throughout the space. So check, you can see the molecule is moving like this, it is going up and down. Okay, so this is what happens in a gas. The molecules are continuously moving throughout the space, so their shape is not fixed. If there is a container in which there is a gas, you just open the cap, the gas will expand throughout the room. Is that right? So three basic differences are there. Basic differences there between these three states of matter. Solid is rigid, okay, but in case of liquid, the shape is not fixed. If you take water from a bucket and you pour it in glass, it will take the shape of glass, but the volume of water is fixed. 1 liter of water, whether it is in bucket or it is in bottle, it will remain the same. And when we talk of gases, neither the shape nor the volume is fixed. So these are some basic differences. But now we are engineers, we are not school students. So our definition, our differences should be at the engineering level. So can you tell me what is the engineer level difference between the three states of matter? What is the technical difference between the three states of matter as according to mechanical behavior? According to mechanics. Anyone? See, what do you do in mechanics? In mechanics you apply forces, and because of forces there will be deformation or motion. So what we want is, we want difference according to mechanics, that is how the substance is going to deform or move, right? Says yes, very good. Example, Dhruv is giving an example. He's writing something like fluids cannot resist shear stress. Very good. So let's have a look at it. Okay. So actually what we are going to do is, we are going to apply shear force on all three substances. I will apply a shear force on solid as well as on fluid. Fluid means liquid or gas. Now when you are applying shear force on solid, there will be some deformation, that is there will be some behavior. Similarly, when we are applying shear force on fluid, there will be some deformation and again some behavior. So difference in two behavior will actually tell us what is the definition of fluid. Okay, I hope you are getting the point. What we are going to do is, we are going to apply shear force both on solid as well as on fluid. So these two substances will show different behaviors, and this is what we are going to check. So firstly, let us apply shear force on a solid substance, and these things you have to note down in your copies. So what we are going to do is, we are going to apply shear force on a solid substance. Okay. Please note all these points, because in this particular topic of what is fluid, we will have 4 objective points which are asked again and again in GATE or IES or DRDO exam. Sometimes when you go for BARC interview, if you will go for interview in BARC, there also these questions are very common. Okay, so please have a look. Now what we have is, we have a solid body, and maybe the solid body is fixed to the ground. So this is your solid body, and here you can mark A, B, C, D. Now what we have to do is, we have to apply a shear load on the solid substance. So this is my shear force, and I think since the body is fixed to the ground, so ground will also apply a shear force in the opposite direction. Okay, now check. I think in strength of materials you studied, or you will study, that if there is a body and we apply shear load on it, so because of the shear load, the shape of the body will change like this. Is that right? So initially there will be some change in shape, but after that the shape will become constant. Am I correct? Am I correct that this is the solid body? Because of the shear load, there will be some change in shape, but after this deformation, the shape will become fixed. Is that correct? Okay, so what will happen? The body will take a new shape, and maybe it is A, B dash, C dash, D. A, B dash, C dash, D. And for this deformation, you will say that there is some shear strain in the body. Now check. So there is some deformation, but after an initial deformation, if the amount of force is fixed, I mean I'm still applying the force. If I will remove the force, the body will come back to its original shape. If I will increase the force, the body will deform further. But if the force is fixed, the deformation or shape will remain fixed. Hai? So basically, the deformation is not increasing with time. Deformation is not a function of time. So what we say is, your strain is not a function of time. This means this is a static deformation. Deformation is there, but it is not increasing with time. So we call it as static deformation. Strain is there, but it is not a function of time. Anyone having a doubt in this? Okay, so basically you can write down directly that whenever we apply shear force on a solid body, it is going to show some static deformation. No need to write down the whole statement. This point is sufficient, I think. Static deformation. That is, phi is not a function of time. So guys, Aditya is asking a doubt. Why phi is not equal to phi of t? Aditya, please check. So there is a deformation. So body will change shape like this. But now the shape is fixed. The shape is not changing with time. Okay. So after some initial deformation, the shape of the body is fixed. Now check, is the deformation increasing or decreasing? No. Deformation is constant. So deformation, what is deformation? It is phi. So deformation is constant. Therefore, it is not a function of time. Okay. Now, in SOM, we also study that whenever we apply shear force on the body, there is deformation in the body, and because of that deformation, there are some internal stresses also. And that's why when we remove the external stress, the shape of the body comes back. The body takes back its original shape. So there are some internal stresses. So let us see how to draw those internal stresses. Paul, what we say, bodies are elastic in nature. So when bodies are elastic in nature, what this means is you take a rubber band and you extend it. But when you will remove the force, the body will come back, the rubber band will come back to its original shape, right? Similarly, I am applying some shear force. So there will be deformation. But when I will remove the force, the body will come back to its original shape. Why? Because of elasticity. Because of elastic internal stress. Do not worry, I am not considering plastic deformation. Okay, I am considering only elastic deformation. So check, what we have is, this is the deformed shape of the solid body. Okay, and basically on this body, you were applying a constant load of F. Now what you do is, you draw a section in the body. I think this is what you do in SOM to denote the stresses. So what I am doing is, I have taken a point in the body. And through this point I am drawing a plane. So basically the meaning of this is that you have divided the body into two portions, portion A and portion B. Okay. Now check, the upper force is directly acting on portion A, and similarly the bottom force is directly acting on portion B. But the entire body is at rest. So if the entire body is at rest, its portion is also at rest. A portion is at rest only if net force is 0. Now how the net force will be 0? B will apply a force on A and A will apply a force on B. Right? This is what you do in SOM. So basically what is happening is that the parts of the body are applying force on each other. Parts of the body. So we call these forces as internal forces. Sanjay, actually materials are of different types. Okay. And what you are talking is, there are different types of behaviors. Viscoelastic behavior is there. Okay. Creep is there. So I'm not talking of that. I'm talking of very basic example that let us say there is a steel block and on the steel block we are applying very small load. So if the load is very small, there will be elastic deformation only. Okay, a very small load is there. So you need not worry about the deformation or anything else like creep or anything else or any viscous behavior. Okay, बहुत basic सा idea ले रहा हूँ मैं तो बिल्कुल fundamental material की बात कर रहा हूँ. Now check. Now these forces, these are the internal forces. So basically this force is spread over the entire area of A or entire area of B. So what you can do is you can denote these forces by force per unit area, that is the shear stress. So here you have some shear stress tau, right? And what is tau? Tau is simply equal to force per unit area. Now we know from experiment or from basic simple observation that these tau are elastic in nature. Why they are elastic in nature? Because when you remove the external force, the body will come back to its original shape. Why it will come back to its original shape? Only because of tau, right? So you can simply say that in solid bodies, tau, that is the internal stress, is elastic in nature. Okay? And from UTM, from UTM you do sigma is equal to epsilon into strain. Similarly from testing, from experiments, you observe that tau is directly proportional to phi. Shear stress is directly proportional to shear strain. So if you remove the proportionality sign, this will become tau is equal to G into phi. Can anyone tell me what is G? Anyone? What is G? And what are its units? Very good. Modulus of rigidity. That is resistance to shear deformation. You can call it as modulus of rigidity or shear modulus. It is simply the resistance to shear deformation. Okay. So this is what is the behavior when you apply force on a solid body. Now the question is, what will be the behavior of a fluid when we apply force on it? Very good. The units can be Pascal, Gigapascal, Newton per meter square, or in other system you can write it as Newton per mm square also. Okay. So now let us apply shear force on a fluid substance. Okay. Now in this case, first of all, the question comes, how to apply shear force on a fluid? I mean, when we want to apply shear force on solid, it is very easy. How? Suppose the block is resting on the ground. So when you will push the block ahead, the ground is going to apply friction force on the block. So this friction force is the shear force, right? But how to apply shear force in a fluid? Are you going to move? How you are going to move your hand or some object in order to apply shear force? So in this regard, Sir Isaac Newton helped us. So what he did is he performed an experiment. So let us see what that experiment was. So maybe that guy, he was standing in a swimming pool. Okay. So this is the ground. This is the base of the swimming pool. This is Sir Isaac Newton. And this is the height of water in the swimming pool. Now what he did is, very good. Deformation is continuous in case of fluids. Now what he did is, he took a very large plate, very large, maybe wooden plate, but it was very thin, okay? It was very thin. There is a reason behind taking a large and a thin plate. Say for example, if I want to talk about thin plate, so I hope you know that whenever a body floats, a portion of it is inside the water. Am I right? Whenever a body floats, the portion of it is inside the water. So what we are doing is we are taking a very thin plate. So almost entirely the body is outside water. Okay. Secondly, we are taking a very large plate because what will happen is we are going to push the plate. So as you will push the plate, the water below it will also move. Okay. So what happens is the motion of fluid here, that is at the end, is different than motion of the fluid here, that is in between somewhere. So if I consider that the plate is very large, I need not consider this. I will consider the motion directly below the plate in the middle portion. I hope you guys are getting the point. Okay, so what we have is we have a plate and the plate is initially at rest. Now check, draw the free body diagram of the plate. So I think on a body, only two types of forces act, right? What are the two forces? What are the two types of forces acting on a body? Very good. Body force and contact force, body force and surface force. Very good. So I think first of all, the plate is going to have some weight, okay? And secondly, the body is in contact with water. Yes, actually there has to be a buoyant force also, but buoyant force is nothing, it is a contact force, it is pressure force only. So when I will go to chapter 2, I will prove that buoyant force is a contact force, it is a pressure force, okay? So what I have is, I have a body, it has some weight and it is in contact with water. So water will apply some surface force on it, okay? And I hope you remember, yesterday we discussed that surface force means two components. One is the normal component and other one is the tangential, that is the shear component, or what you were calling as shear force. So the surface force will have two components. One is the normal component and the other one is the shear component. Okay? Let us write it as small f only. Now what we do? We represent this normal force by force per unit area, that is pressure. And similarly, we represent shear force by force per unit area, that is tau. Is that correct? Is that correct? The normal force is acting on the entire surface. Therefore, normal force per unit area is the pressure. Shear force is acting on the entire surface. So, shear force per unit area is tau. Now, the body is at rest. So, can anyone tell me what is the value of tau? The body is at rest. So, can anyone tell me what is the value of tau? Very good. So, I think by free body diagram, the vertical forces will balance each other, horizontal forces will balance each other. So what you will say, the pressure will balance the weight, okay? But in horizontal direction, there is only one force, that is tau. So if the body is at rest, definitely this tau is also 0, okay? So in this condition, the tau is 0. So this is the information which Isaac Newton told us. Now what Isaac said, that let us do one thing, let us start pushing this block ahead, this plate ahead with a constant force F, okay? So he started pushing the block with a constant force F. Now initially the body was at rest, that means the net force on the body is 0. But now he has started applying an additional force F. So if he has started applying an additional force F, what was the initial force? Net force 0. Now the force is F. So net force is equal to mass into acceleration. So what will happen to the plate? The plate will start accelerating. Am I correct? Am I correct? Initially the net force was 0. Sum of all forces was 0. Now we have started applying another force F. So this plate will start accelerating. So this plate started moving. It was accelerating. This means the speed of the plate was increasing. But after some time, what he realized is that the speed of the plate became constant. Okay? Initially, the plate was at rest. He started applying force on the plate. Because of the force, the plate started accelerating. But after some acceleration, after some time, the speed of the plate became constant. So if the speed of the plate is finally constant, what will be the net force on the plate? If the speed of the plate is constant, what will be the net force on the plate? Very good, it should be 0. Speed is constant. So when speed is constant, acceleration will be 0. Net force is mass into acceleration. So net force should be 0. But you are applying an additional force F. So this net force will be 0 only when there is a non-zero shear stress. Okay? So initially when the plate was at rest, the tau was 0. But now when the plate is moving with the constant velocity, the tau is non-zero. But who is applying this tau? Water is applying this tau. But for every action and reaction, there is equal and opposite reaction. So what will happen? On the surface of water, the plate will apply a shear stress in the forward direction. Sridhar, it is lost against friction in water. This is nothing but friction. Okay? Now check what is happening. When the plate is trying to move with respect to surface of water, a shear stress is developed between them. Okay, so you can simply say, whenever a solid body and a surrounding fluid have relative motion between them, the shear stress will be induced between them. Okay, so this statement you can write down. You can write the statement, whenever there is a relative motion, between a solid surface and adjacent fluid, shear force or shear stress is induced between them. Okay, so basically when water moves inside a pipe, it moves with respect to a solid surface, inner solid surface of the pipe. So there is relative motion between liquid and solid surface, so there will be some shear stresses. When a ship moves in water, so ship means solid surface, water means fluid, so relative motion between ship and fluid, so there will be some shear stresses. Is that clear? So now we know how to apply shear force on a fluid, but our aim is to find out the behavior of the fluid when shear force is applied on it. So let us see what is going to happen to the fluid. What will be the deformation of the fluid? So to understand the deformation, now water is transparent, right? So you cannot see its motion properly, you cannot see its deformation properly. So what Newton did is, he took some colored particles, like a colored dye. So he took some colored particles and introduced those colored particles in water. So basically those colored particles, they got stick with the particles of water. Okay, these colored particles got attached to the particles of water, and when the particles of water were moving, they were also moving together. So Newton simply observed the motion of the colored particles and he could make out the motion of the water particles. Now what he observed is that when the plate was moving ahead with a constant speed u, this is what he observed, that the plate is moving ahead with a constant speed u, then this topmost particle, which is in direct contact with the plate, is also moving with the same speed. Okay, in water what he has done is, he has introduced colored particles. Those colored particles stick with the particles of water. So when the colored particles move, basically they are telling the motion of water particles. Do not worry, today I will give you the definition of particle also. Now what he observed is, from the experiment, that if the plate was moving ahead with the speed of u meter per second, then this topmost particle, which is in direct contact with the plate, is also moving with the same speed. Now maybe Newton performed this experiment with different fluids and at different values of u. But in every case, he observed that this particle or the layer of fluid which is in direct contact with the solid surface, it is moving with the same speed. So what is the relative motion between the plate and this particle or this layer? What is the relative motion between the plate and the neighboring fluid layer? Zero. Very good. This condition is known as no slip condition. And this was an experimental observation. Okay. Now in our course, whatever problems you are going to deal with, this observation is always valid. What is no slip condition? No slip condition simply means that whenever a fluid moves relative to a surface, the layer of the fluid which is adjacent to the surface, this layer sticks with the solid surface and the relative motion between them is zero. What is the relative motion? It is zero. So you can write this statement. Whenever a fluid moves with respect to a solid surface, the particles or layer adjacent to the surface stick with it and achieve zero relative motion. Okay, this is no slip condition. Similarly, this is the ground, this is ground. So the solid particle which is in direct contact with the solid surface. So what is the speed of solid surface? It is zero. What will be the speed of this particle? It will be 0 only. Why? Because it will stick with the solid surface because of no slip condition. So the speed of this particle is going to be 0. Now what I am doing is, on the basis of experiment, what we found out, that let us say the value of u is 1 meter per second. So this topmost particle will also move with 1 meter per second. Now the second particle will move at a little smaller speed. Say for example 0.8 meter per second. Okay. So what I am doing is, I am denoting the velocity of particle by an arrow. So the direction of the arrow, orientation of the arrow shows the direction of motion, and the length of the arrow shows the value of speed. Okay. So this is the speed of second particle. The third particle was moving at even lesser speed. The next particle at more less speed, the last particle at more less speed, and this is how the velocity of these particles look like. This was an experimental observation only. Now what you do, you take a coordinate system. This is the x direction, this is the y direction, and what we have is, we have a particle which is at a distance y from the bottom. Which is at a distance y from the bottom. Now can you tell me what is the direction of motion of this particle according to experiment? These are all experimental observations. What is the direction of motion of particle? I think it is x direction. So along the x direction, this velocity component is written as u. Is that right? Whenever you talk of velocity vector, the velocity vector has three components. One is u, v and w. U is the velocity along x direction, v is the velocity along y, and w is the velocity along z direction. So this particle is moving along the x direction, so it is going to have only one component, which is u. Now compare two particles. So this is your particle 1 and this is your particle 2. Now check, are the speeds of two particles equal? Are the speed of two particles equal? No. So basically what you can say is, if the distance of fluid particle from the solid surface is different, its velocity is also going to be different. So particles which have different y will have different velocity. If the y is different, the velocity will also be different. So you can simply say that u is a function of y. Am I right? If the value of y is different, the value of u will also be different. So u will be a function of y. And this figure which you are drawing, this figure is known as velocity profile. Velocity profile, or very well said by someone, velocity distribution. But better name is velocity profile. Velocity profile simply tells you what is the velocity direction of a particle. What is the velocity of a particle? Okay, so this was his observation. And have a look at this video. In the video, actually the resolution of video is not so good. The video quality is not so good, but actually what we have is, we have a ground, okay, and above ground water is flowing. Now in the water they have inserted a needle. Can you see a vertical probe? Basically it's a needle, and through that needle they can inject dye in the water. Okay, so what they are doing is, there is a probe and they will take the probe down. So check, they have taken the probe down. Okay, they are touching it with the ground, and now from the probe they will start injecting the dye. Okay, and once they are injecting the dye, they will lift the probe again. Okay, so what will happen? They will insert some particles over here, some particles over here, some particles over here. Okay, so main purpose is to distribute the dye particles in moving water. Now check, this is what they are doing. So the probe is going to go up now, and the dye is also coming out. Check, they are releasing dye particles at different locations. Now have a look. If you consider the bottom, some dye particles are sticking with the ground. The dye particles which were inserted at the bottom are still sticking with the ground. They are not moving. Am I right? So there is some no slip condition. The particles which were inserted over here at the bottom, they got stick with the ground and they are at rest. So there is some no slip condition. But the particles which are inserted over here are moving, okay? And check. If you can see the movie properly, if you can observe properly, the particles which are here are moving slowly, but particles which are here are moving more faster. Just depicting that u is always a function of y. The particles which are away from the solid surface, they move with greater velocities, and particles which are near the solid surface, they move with less velocity, less relative velocity. Is it understood? Is the video understood? Anyone having a doubt in it? Please ask.